Okay, it's time to apply moles of stoichiometry where it really gets use. And so what we're going to do is apply moles to reaction to stoichiometry. And this can be part one. There's going to be several other Blackboard, PowerPoint videos relating to this. Again, this is the most you use the most math in all these, and we'll talk about the math, but also talk about how we try to make math. First thing is grouping, and I just want to go over this because I think grouping is important to understand when you talk about the mole and other things. Is I know, and if you guys are supposed to have had another chemistry course, and you probably were taught dimensional analysis. But dimensional analysis to me is a method, it's a technique, and it's good and it works, and etc. And I use it often, okay, especially when I don't have to think, okay. I know what to set up, and I come up with my answer, make sure my units are okay. But when I have to think, dimensional analysis doesn't really do the trick, and so I'm pretty keen on this because I spent many years teaching, and trying to get this mole concept across the students, and it's been hard. And there's many teachers out there that just teach it from the book, teach dimensional analysis, and I know absolutely for sure that there's a lot of chemistry teachers that probably don't understand really the mole concept, okay, and if they do, they have a hard time explaining what it means. They may be able to explain what it means, but then they can't change that explanation into math, and so that's always been a big thing that I want to do in my career as teaching, is how can you marry math with concept. And so the way I found out to do that is to use groups. So I will be using groups a lot, but it doesn't mean that you can't use dimensional analysis, and I'll show you how they relate as we go along, okay. The main thing is get the right answer and to understand it. Okay. So what I want to do is I want to go over division and multiplication and how it pertains to grouping. Okay. Dividing is just not a math term when we talk about grouping. When we put things in a group, we divide them up into groups. Okay, this is the key thing right here. We divide into groups. Okay, so what you do is you have something and a lot of things, and then you divide it into groups. Okay, all right, and then you'll end up with so many groups. All right, so if you have 100 items and you want to them groups of 10, you divide them up into groups of 10. So this is I have 100 things here, and what you do is you divide it up into groups of 10, and when you do that, of course, you end up with 10. Okay, so you divide. So when you want to get groups from items, you divide. Now multiplication is the opposite. You're ungrouping. So if you have 10 groups of 5, so if you have 10 groups, 8, 9, 10, is that 10? 1, 2, 3, 4, 5, 6. Okay, and each one of these circles has 5. And what you do is you empty out, okay, 5 from each one. You're going to have 50 items, okay? And so what we did is we emptied out, all right, of the groups, 5 items 10 times. So the key term here is actually out, which is the opposite of in. And actually 2 is the opposite of. Okay, so it's interesting how we speak math, and the math that we speak actually tells us what dividing and multiplication do in terms of groups, right? So times is multiplication. So when I say empty out of the groups 5 items 10 times, that's multiplication. So ungrouping is multiplication, and so I'll be using this a lot. The key is to know your group and grouping size. How can you determine if you have a group? So you need to listen. For instance, here's a group, 10 items per box. This tells you that the group is a box, and the items are what's going to be grouped. And the grouping size is 10 items per group. Okay. Now, if you look, this has a per statement. So anytime you have a per statement, it will be a group, where the numerator is the thing to be grouped. That's also known as the divisor. And the denominator, divider, is the group. Okay, I think items to be grouped. Right. Now, you don't try to memorize this. It should make sense. For instance, if you have 1,000 milliliters per liter, that means there's 1,000 milliliters in 1 liter. Okay, so here's a liter, and inside that are 1,000 little milliliters. Okay, density is another good example, and let's look at density of silver. So our density is 10.5 grams per centimeter cube. So if you have a centimeter cube, okay, and it's silver, it's going to have a mass of 10.5. So inside this cube here is 10.5 grams. Okay, in math we substitute the word per with a hash, dividing mark. Okay, so we could also write it as 10.5 grams slash centimeters cubed. Now, I told you groups are everywhere, especially in chemistry. I told you moles are groups. You could have moles as an amount, such as 6.02 times 10 to the 23rd atoms per mole. That means if you have 1 mole of substance, you're going to be 6.02 times 10 to the 23rd. Or in terms of relative mass. So if you have 1 mole of water, okay, so if you have 6.02 times 10 to the 23rd waters, it's going to weigh 18 grams. So inside 1 mole of water, so this is a container of water, a mole container of water, it has 18 grams of, weighs 18 grams. Also, remember it has 6.02 times 10 to the 23rd. The other thing is that grouping sizes are exactly the same as conversion factors, okay? So this guy right here can also be used in dimensional analysis as a conversion factor. Okay, so I'm not doing anything different, okay? It's just applied differently and stated differently. Okay, let's go over a couple grouping operations using density of silver. If I have 5 centimeters of silver, how many grams that is? Okay, so the way I like to think about it is I have 5 centimeters cubed of silver. And each one I have 10.5. Okay, so what do? I do 10.5 5 times. Right, so I'm ungrouping. So here's my group. So I'm going from centimeters, which is my group, to my items. All right. So I do 10.5 5 times for 52.5. Okay, so now the other way. So let's say I have 210 grams of silver. So what I'm going to do is find out how many centimeters cubed that is. So what I'm going to do is divide this up into groups of 10.5 grams per centimeter cubed. Okay, and when I do that, so I'm going to divide the 210 grams into groups of 10.5, and we get 20 centimeters cubed of 20 centimeters cubed. Okay, and you could check your answer. So if you have, see if you get back to 210. If you have 10.5 grams per centimeter and you have 20 of them, well, that's going to be 10.5 20 times, or 210. Okay, so the main thing, so one thing I'm going to talk about a lot, make sure you know your group. Okay, if we're going from a group to an item, number of items, you're going to multiply. You're going to let them out. Okay. If you're going the other way, if you're grouping, okay, you're going to divide. All right. So you don't have to do it this way. You can use dimensional analysis, but I just like to make things simple. Say I'm going to divide my things into groups. I'm going to let my groups out and multiply. So if you notice my language in the above, for dividing I use in, sometimes into. And for multiplication I use out, or sometimes out to or from. I mean, it should be out of. Okay. 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 And it turns out that actually of is the opposite of to, and as well as from. It's the opposite of to, at least in how we use it. The bottom line, when looking at group size, the divider, so if you have two things like this guy down here is going to be your group. Okay, and these are your items to be grouped. Okay, and this whole thing is the grouping side. So to group, you divide up, and to get items, you multiply out of. All right. Now, to reaction stoichiometry. Now we're going to apply moles to chemical reactions. A chemical equation is more than just showing what happens in a reaction. It also tells us how to make the product and the very specific amounts of the reactant and product that are used. I like to call chemical equations recipes. This is because this is what they are. They tell us what reactants and how much of them are to make a specific amount of product, just like a recipe does. Okay, basically, a chemical equation is a cooking recipe. You are given the recipes, the ingredients, the proportion of the ingredients, and the outcomes you want. So before we get into chemistry, just make sure we understand what recipes are and how it relates to proportion of the materials. So this is a real simple one. I don't even know if it works, but suppose I have a recipe to make pancakes. The recipe goes like this. 3 cups of flour plus 1 cup of sugar plus 2 cups of eggs plus 1 cup of milk will give me 3 cups of pancake. The left of the arrow essentially is the reactants, and the right side is the products. Okay, just like in chemistry. All right, the numbers in front, the coefficients, okay, are the coefficients, and they represent relative proportions. In this case, cup per recipes. So in the recipe it says to do the recipe, you need 3 cups of flour, or you could write it like this. 1 cup of sugar per recipe, like this. 2 cups, and so forth. Okay. Now notice you have a per statement. That means we have recipes as our group, and pancakes, cups of pancakes as our items. So what we're doing is our grouping our cups into recipes. Okay, so let's see how we do this. So here's the equation: 3 cups of flour, recipe, and so forth. Okay, so let's say I want to do 3 recipes. How much flour I'm going to need? Well, you can see it's fairly simple. So every recipe, I need 3 cups of flour. I do that 3 times. So I have 3. I'm going to empty out 3 cups of flour 3 times for 9 cups of flour. Okay, and so what I did was I started out with, I have 3 recipes, and each one has 3 cups of flour, and then I let them all out, and then I end up with 9 cups of flour. Okay. Okay. so we have to be careful. Now I want you to pay attention to my wording. Okay, is 3 times 5 the same as 5 times 3? Well, in math it is. Okay, it's called the commutative property. Okay, it doesn't matter which side you put 3. 3 times 5 is equal to 5 times 3. Okay, but when we talk about grouping and ungrouping, I think it actually does make a difference. Okay, so the way that I just say the above kind of thing was I said 3 cups per recipe, and I want to do the recipe 5 times. The way I say is do 3 cups 5 times. I'm not going to say do 5 times 3 cups. Okay, I mean, you might, it's just awkward to say that. Okay, so I will, when I say my words will make sense to me. Now your brain might switch them to say 3 times 5 equals 5 times 3, but pay attention to my words. Like when I say divide into or multiply out of, okay, these words have taken me a long time to make careful on how I'm explaining things. So let's do a grouping. So here's a sample problem again. Let's say I have 28 cups of eggs and I want find out how many recipes is. Okay, from the previous, I know that, well, from down here I have it. So there's 2 cups of eggs per recipe. So if I have 20 cups, how many recipes can I get out of that? Well, I can just divide the 20 cups up into, okay, 2 cups per recipe for 10 recipes. Okay, so ungrouping and grouping. So when you ungroup, you multiply out of, and when you divide, you divide up into. All right, now what we're going to do is kind of show that up and down out of using a table. Okay, so what we're going to do is rewrite that equation, and you put it in what I call a recipe table. Okay, so what I have here is, here's my substances. Okay, and I have recipes, cups per recipe, and cups. And so recipes and cups are related by this guy right here. And here's this coefficients go where the cups of recipes are. Okay, for every time I make these pancakes, I will have this table. So let's use this table. All right, how many cups of eggs will be needed for 4 recipes? So I'll put the 4 here. Okay, I'm going to do the recipe 4 times. Every time I do the recipe, I need 2. So I'm going to do 2 4 times. So if you heard my language, I just said 2 4 times. So I multiplied. Okay, I ungrouped. So the recipes are my group. Okay, so groups are up here, items are down here. So I ungrouped and I multiplied. So I basically ungrouped 2 cups per recipe out of 4 recipes. I end up with 8. Okay, so to find number of cups, I emptied down out of each recipe 2 eggs. I do that 4 times. So the way I actually drew it, I explain it, use words to explain it. I say I emptied down out of 4 recipes, okay, and 2 eggs, and end up with 8 cups. So we're going to be using this table a lot. This kind of table is going to be big deal. Okay, so let's use it again. So this time we're going to start out with 12 cups of flour. All right, each recipe needs only 3 cups of flour. So how many cups can I get out of 12? So I can divide the 12 up into groups of 3 for 4 recipes. So I can do the recipe 4 times. Okay. So I divided the 4 cups into groups of 3 for 4 recipes. So going up the table, you're grouping, dividing up, and then when you come out of the table, going down, you're multiplying out of. So going up, you're putting it into groups. Going down, you're ungrouping. Try another one. Okay, this one's a little bit more complicated. This one says you have 30 cups of eggs and you want to know how many cups of pancakes. So this one's actually 2 steps. So you start out here. Okay, so you got to think about what you're going to do. So look, the table will help you think about it. So first thing, you have 30 cups, so you need to find out how many recipes. Bring that over here, and then from the number of recipes, you can figure out the number of cups of pancakes. So first thing I'm going to do is figure out how many recipes. All right, so I can divide the 30 cups into groups of 2 for 15 recipes, and that's right here. Now I bring that over here because it's the same. And then for every recipe, I get 3 pancakes, and I do that 15 times. 15 times. And I end up with 445 pancakes. Okay. No, I didn't use anything about multiplication. I just said 3 times. I didn't say down, out of, or anything like that. I just said 15 times. But over here, I said divide it up in 2. The words have to make sense. All right, and now here's some problems you can do on your own. All right, now to chemistry. How to apply to chemistry. I said a chemical equation is nothing more than a recipe. Let's see how. So here's a balanced equation for combustion of propane. Now this looks quite a bit like the pancake recipe, okay, where it has numbers in front of our ingredient. But notice we don't have anything here. You could put cups, but we don't use cups in chemistry. Instead, we will use molecules, atoms, or moles. So let's go down the very basics, what it means. So this says 1 molecule of propane plus 5 molecules of O2 will give me 3 molecules of carbon dioxide and 4 molecules of water. So I probably should have wrote this 5 molecules of O2, but kind of slipped there, but you know what I mean, hopefully. I could also write it as 1 dozen molecules of propane plus 5 dozen O2s give me 3 dozen and 4 dozen. The main thing in here is the proportion stays the same. You can write it as 1,000 plus 5,000 gives me 3,000, 4,000. It's the same ratio as 1 to 5 to 3 to 4. You could do 1 trillion to 5 trillion to 3 trillion to 4 trillion. Still give me the same proportion. And then finally, the one that we use is that 1 mole plus 5 moles will give me 3 moles plus 4 moles. 4 moles, okay. Right, where a mole is 6.02 times 23rd. Okay, just let you know, we really won't be using this number probably again in the class. They just use it for the problem set that we had we just got done with. May, but probably not. So moles are preference because moles are amount of molecules or atoms that we can physically manipulate. For instance, 1 mole of water weighs 18 grams. And I can easily measure that out. I have a scale that can measure out grams. So moles are preferred to use in our recipes. Okay, so what I can do is write that equation as a recipe table, but instead of having cups, I have moles. Okay, this again represents the coefficient represents moles per recipe. Okay, we're going to do problems relating to this. So let's apply it. So the first problem says, how many moles of oxygen can I get from 12 recipes? Okay, the recipe says 5 moles per recipe, and I do that 12 times, so I end up with 60 moles. Okay, simple. You're emptying out 5 moles every recipe, and you do that 12 times.
GPS signal lost.
What was that? Oh. Okay. All right, how many recipes do we need to make 40 moles of water? Okay, so start off with the 40 moles of water. Then see how many recipes you need for that. So you have 40 moles. Every recipe you need 4 moles of water. So you can see that you can get a lot of recipes out of this, okay? So how many recipes can you get out of 40? Well, you just divide the 40 up into groups of 4, and you end up with 10. Okay, hopefully it's pretty simple and it's pretty neat that you can see what you're doing. Now, if you want to do dimension analysis, you would say 40 moles, okay, times the 1 recipe per mole. I mean 4 moles for 1 recipe per 4 moles, which is awkward, but it'll give you 10 recipes. Okay, so this is your conversion factor. One thing that if you're doing dimension analysis, what you'll notice is that when you divide, so when I group, I say divide up into, okay, so I divide by the grouping size. But if you're using dimensional analysis, what you do is actually take the inverse of the grouping size to use. So if you notice, this is the inverse. Right? I don't know if you just got that, but it's just what I'm saying. If you're going to use the dimensional analysis, you take multiply by the inverse of the grouping size. Now, if you're doing it the other way, if you're ungrouping, you keep the grouping size the way it is. All right, so how many moles of carbon dioxide can be made from 5 moles of propane? All right, so I have 5 moles here, and I want to know how many, so every recipe, so I'm going to first figure out how many recipes. So every recipe, I need 1 mole. So how many times can I do that? I can do that 5 times. Okay, every recipe, I need 3 moles. So I'm going to do that 5 times for 15. Divide up and multiply. Okay. So whenever you're going to be doing stoichiometry, write out the table. Okay, because what you're going to be doing is figuring out moles, going to recipes, okay, and then coming back out of moles. All right. But this table is going to be your central processing unit in a sense. Is you got to put things in, and then you got to have things come out. Now, things that come out will be things like grams, volume, pressure, density, moles per liter, etc. Because we can't measure moles directly. We can only measure, what we can do is measure the relationship. And we'll talk about that in a few. Like right now. Okay. Now, considering different states of matter. So, when we do chemistry, we can't measure moles directly. What we have to do is measure like grams. Okay. But once you figure out grams, from the material we just went over, if I give you a certain amount of grams, you can figure out the moles. Okay, and once you have moles, you can use the recipe table. Okay, and so what we're going to do is be going over that. So, what we're going to do is use the equation that I have, the combustion of propane. And just want to let you know that I kind of made an assumption that's probably not right. I'm going to assume that everything's a solid. But everything's actually a gas, but it doesn't matter because you actually can measure the mass of a gas. But usually we use molar mass when we want to figure out solids. We're going to have a different way of measuring gases, which we'll get into. But I'm going to use the mass and for our substances. So anytime once you know the state that you're using, you will have some relationship between the state and how it relates to moles. And for solids, the relationship is grams to moles, or molar mass. Okay, so anytime you do come up with your recipe table and you're to find grams, write out the molar masses. Okay, so I have the molar masses here, and we're going to be using these. And these are easy enough to find. So molar mass of propane is 12 plus 12 plus 12 plus 8 hydrogens are 44, and I'm rounding the nearest whole number. Oxygen is 16 plus 16. Carbon dioxide is 12 plus 16 plus 16, 44. It's just coincidental that these numbers are the same. And then water is 18 grams per mole. So I'm going to use this right here and my recipe table to figure out my problems when I measure mass. And that usually is solids, but it doesn't have to be, but usually solids. Okay, so example 1, suppose I want to know how many grams of oxygen will I need for 5 recipes. Okay, now, so look at the table. Notice the table has moles and recipes. It doesn't have grams to recipe relationship. So what we have to worry about is that, first of all, we're given 5 recipes. So we can't worry about grams. So what we have to do is that given grams, I can figure out moles. And then once I figure out moles, I can figure out grams using molar mass. So I put the 5x here. So I can do it 5 times. Every time I do it, I need 5. And so that's going to be 5 times, or 25 moles of oxygen. Okay, every mole of oxygen weighs 32, and I do that 25. So I'm going to end up with 800 grams of oxygen. Okay. And you could use dimensional analysis for this as well. That doesn't matter, so it's, you'll say. But, make sure you got your units and make sure you can show me how it's done. Actually, just writing it out like I do is fine. All right, example number 2. How many recipes are needed to make 660 grams of carbon dioxide? Okay, again, the tables is in moles and recipes. So you have grams. So what you got to do is you got to figure out how many moles of carbon dioxide. Okay, you know the molar mass is 44 grams per mole. All right, so you have 660 of them. So we divide the 660 into groups of 44, and you end up with 15 moles. Okay, every time you do the recipe, you need 3. So how many recipes can you get out of 15? So you divide the 15 into groups of 3, you get 5 recipes. There you go. Okay, example number 3. How many grams of water can be made from 220 grams of propane? Okay, now this one is, the table's not even in this. Okay, you have grams and grams, you don't have moles or recipes. Okay, but what you got to do is you have to get into the table, okay, because that will tell you the recipes, and you need to find recipes. So the goal is to find out how many recipes 220 grams of propane is, and then you can figure out how many, from that you can figure out how many moles of water. Okay, so let's think about this. We have to figure out how many recipes 220 grams of propane can do. So we need to figure out how many moles of propane that is, and we figure that out from the number of recipes. Once we know the number of recipes we can make from 220 grams, we can figure out the moles of water. Okay, and then from there, you know the molar mass of water, you can figure out how much it weighs. So it's essentially 4 steps. First thing you do is you're going to find out how many moles of propane from the grain, and you're going to use molar mass. Okay, next thing you'll do is use moles of propane to figure the number of recipes. Again, and then from the number of recipes, you can figure out the number of moles. And then from the number of moles of water, you can figure out the grams. And let's look at how are we going to do this. Good. The first thing to do is figure out the moles of propane from 220 grams. Well, every mole of propane weighs 44 grams. You have 220 of them, so you divide 220 grams up into groups of 44, and you will end up with 5 moles of propane. Okay, next step. Now we can put it into the table. Okay, and that's, we can do step 2 and 3 for the table. So now what we're going to do is divide. So every time you do the recipe, you need 1. So obviously if you have 5, you can do the recipe 5 times. So bring that over here. Okay, so how many moles of water? For every recipe you'll get 4. You can do that 5 times, so you end up with 20 moles of water. And then lastly, okay, so you went 220 here, and you got to figured out the molar mass. Okay, did all this, and now you want to get this in the grams using molar mass. And so every gram of water every mole of water weighs 18. You can do that 20 times, and so you end up 360 grams. Okay, so now it's up to you. I want you to give these a try, see how you do on them, and see if you get the answers that I say here. Okay, and there'll be worksheets related to all these. The next videos are going to be how to use the different states and applying different problems. Okay, so okay, that's all.